In our universe, the laws of physics tell us all the possibilities for what's allowed to conceivably exist, but only by actually observing, measuring, and experimenting with our universe itself can we determine what's truly real. In Einstein's general relativity, one of the very first possibilities that was ever discovered was for a black hole, a region of space with so much matter and energy in one place that from within that volume, nothing, not even light, could ever escape. The flip side of that is an equally possible mathematical solution that's the reverse of a black hole, a white hole, from which matter and energy will spontaneously emerge. Black holes have been demonstrated, through many different types of observations, to not only be physically real, but to be quite abundant all throughout the universe. What about white holes? What are they, and are they physically real too? The idea of white holes makes a lot more sense if you begin with its much more familiar counterpart, the black hole. First thought up in the 18th century by John Michell, who referred to them as dark stars, it was realized that just as all masses in the universe have an escape velocity from their surface, for example, there's a certain speed that one must reach to escape completely from its gravitational pull, that if enough mass is gathered in a small enough volume, that escape velocity would reach or exceed the speed of light. Since nothing can move faster than that speed, these objects would only absorb light and matter, but would never emit any from within a certain distance, its event horizon. The original idea was put forth within the context of Newtonian gravity, but in 1915 Einstein's general theory of relativity was released, superseding Newton's and replacing it with a more comprehensive law of gravity. Nevertheless, black holes persisted. They were shown to arise within Einstein's theory as early as 1916, and versions of black holes with electric charges and angular momentum as well as mass were also discovered. Once again, with enough mass in one region of space, the creation of a black hole would be all but inevitable. So, if black holes are real and abundant, what prevents white holes from being just as prevalent? Could they be lurking in the shadows, hidden by the very laws of physics that predict their existence? Or are they simply a cosmic curiosity, a mathematical anomaly that we are yet to fully understand? So, if that's a black hole, then what is a white hole? There are two ways to look at it. One is to simply recognize that general relativity is a time-symmetric theory. If you observe a system of matter and energy in motion through the fabric of space over time, you cannot tell whether the clock is running forward or backward. General relativity's predictions are symmetric in time, meaning that objects move, accelerate, and interact according to the same laws in both cases. This applies to even bizarre cases. Two black holes orbiting one another in a decaying fashion and emitting gravitational waves obey the same physical rules as two black holes that orbit one another and absorb gravitational waves from their surroundings, getting farther and farther apart over time. A cloud of contracting matter that fragments into clumps that will eventually form stars obeys the same rules as a series of expanding clumps of matter that move apart from their points of origin and diffuse into a large, fluffy cloud. And matter that collapses to form an event horizon and then a singularity, a black hole, obeys exactly the same rules as a singularity from which matter and energy, as well as space and time, emerge. Considering the case of a time-reversed black hole is one powerful way to conceive of a white hole. But there's another way to think about white holes that stretches beyond mere time symmetry. Imagine a realm where what falls into a black hole re-emerges from a white hole. For instance, in theoretical models like the Einstein-Rosen bridge, commonly known as a wormhole, a black hole could connect to a white hole, forming a tunnel through space-time. This would mean that what enters a black hole could potentially travel through a wormhole and exit from a white hole, albeit in another region of space or even another universe altogether. Another way to think about a white hole isn't to reverse the arrow of time, but rather to think about what happens if you treat space as reversible. Before you scratch your head wondering how such a thing is possible, be aware that we have an analog of that in the real world, a spherical, mirrored orb. If you were to put a spherical mirror in space, you'd be able to see a reflection of the entire exterior universe in it, simply by looking at the mirror from the right perspective. Well, the space-time inside and outside of a black hole's event horizons behave very analogously to exactly that situation. If you consider a black hole that's defined only by a point mass, a Schwarzschild black hole, then for whatever value of mass energy the black hole has, we can also define a specific radius. We call it capital R for the black hole's event horizon. You can ask all sorts of questions about how space behaves at any distance from that black hole, and we can call that distance small r instead. There are now 3 cases r greater than capital R, which places us outside the event horizon. Second case, both are equal, which places us at the event horizon. And small er smaller than capital R, which places us inside the event horizon. Now here's the tricky part, reversing space. What this means then is that if we pretend a black hole is flipped inside out, so that every point from the inside of a black hole's event horizon, including its singularity at small r equals 0, now corresponds to a point outside of a black hole's event horizon, where the singularity now goes everywhere at small r equals infinity, and vice versa. We recover the identical behavior. The only difference is what was outside is now inside and what was inside is now outside. It's just reversed. Instead of a black hole, this flipped object can now be thought of as a white hole. Could these enigmatic objects be gateways to other universes? Imagine for a moment that every black hole in our universe is not just a singularity, but a bridge to another, entirely separate realm. This concept leads us to the fascinating theory of the multiverse. In the multiverse hypothesis, our universe is just one of countless others, each with its own unique laws of physics, constants, and dimensions. When matter and energy fall into a black hole, they could be transported through the singularity and emerge from a white hole in another universe. This idea suggests that black holes are not just destructive forces but also creative ones, potentially giving birth to new universes. Consider the implications. The birth of our own universe might have been the result of a white hole from a black hole in a parent universe. This cyclical nature of creation and destruction could mean that the multiverse is an ever-evolving tapestry of interconnected universes, each influencing and giving rise to the next. Physicists are currently exploring these ideas through the lens of quantum mechanics and general relativity, seeking to understand if our universe's Big Bang was indeed a white hole event. If this theory holds true, it would revolutionize our understanding of the cosmos and our place within it. But do white holes actually exist? The truth is we've never seen one, and we don't expect to ever find one within our universe. Event horizons, unfortunately, are very good at hiding whatever else occurs on the other side of them. There may be something very interesting at the central locations inside each black hole in our universe, but we'll never be able to access them. There may have been something very interesting occurring in whatever birthed our universe before the onset of cosmic inflation and its aftermath, the hot Big Bang, but we have no way of obtaining any information about that time. The sober truth, as much as we might detest it, is that the amount of information present in the universe is finite, and renders us unable to reconstruct what's going on or what went on the other side of these events. It's worth keeping in mind that general relativity admits white holes as an equal possibility to black holes, but that only the observational evidence for black holes has been found within our universe. While mathematics can tell you the possibilities for what could occur, only observations, measurements, and experiments can tell you what does occur within the universe.